All right, so ladies and gentlemen, at the end of our last video, we started talking about the idea of a parallel circuit, which is basically a circuit that has multiple paths for current to travel through. All right, and I kind of tasked you to go into the circuit construction kit and actually build a parallel circuit. All right, so the easiest way to do that is honestly, whenever you're trying to build a parallel circuit, is start with kind of the closest loop and just kind of work your way out. So looking at this, the first little thing is you start with a battery. All right, then you start with some wires. And then basically, you kind of start by making the first branch. So the first branch, honestly, would look absolutely no different than this. All right, it would look no different than this particular setup where you have the wires going through the light bulb, all right, and making what appears to be a series circuit. The parallel circuit comes into play though when we look at the next piece. So you notice the next piece, if I followed the path of the electron, the first path I could do is I could go through here, through this loop, go down this branch, and keep going. All right. Now, a good question would be, well, why doesn't it go through the other light bulb? What we're going to find out is that in this particular setup, electrons always try to go the path of least resistance, and if they're going to be pushed through this way, they're going to run into other electrons. That's going to be a problem. Okay. And what I mean by that is that if we look at the second path, this electron now goes down this pathway. It's going through here. All right. Which means you're going to have a lot of electrons going through here, a lot of electrons going through here. They're not really going to enjoy running into each other, so they're all going to kind of keep moving towards the battery. All right. So to set that up, what we do is basically we would take some more wires, and I'm going to cut this to make it just look a little bit easier. But basically, I make the second setup. All right. And then I just take this other little light bulb and I hook it up. And now, what I have done, and I know it's not super easy to see because it's kind of condensed together, but I've actually created a situation where I now have two light bulbs that are in parallel with each other. All right. Now, this is a rather interesting setup because of what it allows us to do. All right. Now, you'll notice if we look at our little setup, we've got multiple branches for the current to go through, which means actually, in theory, if one of these light bulbs burns out, that doesn't necessarily mean our circuit's dead. Or if I take one of the light bulbs out, it doesn't mean the current's going to stop flowing. All right? Because what we find out is that if I have multiple paths, if I have something in parallel, if one of the branches stops working, the current all just says, oh, well, I guess I can't go through this anymore. So they switch to the other branch. All right? So in this case, in a parallel circuit, the current makes a choice and it splits. All right. Now, this is referred to as something we call the junction rule. So the junction rule for current, and this is going to go under how voltage and current work for parallel circuits. All right. So current in a parallel circuit will actually split off. All right, it makes a choice, and the electrons will split between the different branches. That's just pretty simple. There's only two branches, so the current's only going to split between one or two branches. More complex parallel circuits can have a lot of branches. All right, but what happens is basically the junction rule for the current says that in parallel, all right, the current splits depending on path of least resistance. And what's going to happen is that if you look at the current in each path, if you add it up, the current in each branch has to equal the current that went into the junction. So what I mean by that is that the total number, the current that went in to this little junction right here, when it splits, the current going through this branch and this branch has to add up to equal the current that went into the branches. And vice versa, it also has to mean that the current leaving these two branches has to equal the two of them added together. All right? It's exactly the same thing if you have a river that gets split by an island. Half the river goes on one side, half the river goes on the other. For those split little places right there, the current would actually be much smaller if you only looked at one side. But when they came back together at the end of the island, the current between the two rivers would add up to equal the current before they met the island. Okay, so the junction rule, current splits between the paths of least resistance, but the current in each branch So it adds up to equal total current. All right. Now, voltage in parallel does something rather interesting. All right. So while voltage in series has a series of drops that they're going through, all right, basically like a waterfall that's been broken up into, different little sections as it keeps falling. Voltage drops in parallel are actually almost like two side-by-side waterfalls. All right. And what that means is that as we go through the circuit, all right, remember we talked about the idea that by the time the electron gets to the end of the circuit, it has to lose all its voltage. Well, if I'm going around this first loop, all right, I only drop through one thing, which means according to the electron that goes through this loop, I have to drop all my voltage right here. All right. But if another electron picks this path, it says, no, you're wrong. I have to drop all of my electrons here, or all of my energy, because this is the only thing that's using energy right now. So what we find out is that when things are in parallel, all right, they actually have the same voltage drop. All right. So it would be the equivalent of kind of like, let's say you had, once again, going back to the toll booth analogy, let's say you were going down the highway and you got to a toll booth and there were several toll booths all next to each other. All right. They all have the same toll to get through, but you only go through one of them. All right. And that's exactly how voltage drops work in parallel. All right. So for voltage drop in parallel, basically what we say is that each branch drops the same amount of voltage. So if I had 8 branches here, all next to each other, they would all drop whatever the voltage of the battery was. Okay? In this case, remember once again we said this is a 9-volt battery, so this means that both light bulbs actually drop 9 volts. All right? And you'll notice if we look at it, the brightness is actually different compared to it was originally. So let's say I cut this light bulb out. All right? And I decide to put it in series instead. The brightness is now significantly diminished, because what we're going to find out is because it's all in series, the resistance has kind of changed a little bit, as opposed to when this is in parallel. All right. Now, and I know there's a ton of information I'm telling you about circuits right now, and I know there's a lot of confusing things going on. Please come talk to me in office hours or send me an email if you have a question, and I'll do my best to explain it. All right. Now, in parallel, resistors act in a rather interesting way. All right. And what I mean by that is because, let's say, we talked about in series how resistors act like one bigger resistor when they're all in series. But if we're going back to our toll booth analogy, all right, if I have resistors in parallel, what happens is I actually now have multiple paths for the current to flow through. And what happens is that now it almost acts like I've widened my river, or I've widened my toll booth, okay? Because I've put in more toll booths next to each other, so I have more options to go through. So even though I could have several very high resistors all in parallel with each other, what I've done is by giving the electrons multiple paths to go through, they're actually able to move through faster than normal. So in fact, resistors in parallel actually act like a smaller, weaker resistor. All right. So once again, in parallel, and we can see it kind of right here, but in parallel, the resistors act like a weaker resistor. All right, because now they have multiple paths. And I apologize for my misspellings in all these videos. That's what happens when I'm doing it on the fly here. Has multiple paths to travel through. Okay. Now, unfortunately, there isn't a really fun way to figure out resistance in parallel. In fact, it has a rather ugly formula, and what it looks like is the following: that the equivalent resistance of all these things in parallel looks like this. And it looks like 1 over the equivalent resistance is equal to 1 divided by the resistance of the first thing plus 1 divided by, excuse me, the resistance of the second thing, plus da 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 da, over and over, however many of these things that you have, these resistors you have in parallel. All right, but it looks kind of ugly, I know, but at a fundamental level, all it means is that if I take two things and I put them in parallel with each other, right, according to my circuit, I have actually made the resistance of the whole circuit less. So actually more current is going to start flowing through it because I've given the electrons a better chance to move through it and not run into other electrons. Right? Now, of course, with all these things, we don't just only have series and we don't just only have parallel circuits because each of them has benefits and each of them has drawbacks. All right? Instead, what we normally see is we see something referred to as a combination circuit. All right? And a combination circuit could look something like this, where you have things in parallel and in series. In this case, looking at this circuit, it starts with a battery. It goes through, reaches a point where there's actually a little box here. So there's two branches for the current to flow through. So this would be a section that's parallel. But then all of it comes together, and then it all flows through this resistor right here. And the reason we use these is because they give us particular things that are useful. In this case, all right, maybe I have, in this particular case, maybe I have a setup where I need lights that I can turn on and off at will, or if one of them burns out, it won't mess up the other one. But I also have a situation where I have maybe a circuit breaker or something here that I want set up that ensures that everything's working properly. All right. So in this particular case, a combination circuit is just a combo of series and parallel. And what we're going to find out is that in order to look at this type of circuit and break it down, and if you go into electrical engineering or you kind of go into more advanced circuits, you're going to have to simplify a circuit like this. All right. And we're going to find out is you just combine the rules of series and parallel. And we're going to talk about that in the next video. All right. So it's just literally a combination of series and parallel circuits.